Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. The Allais paradox. Maurice Allais, a French economist and Nobel laureate, presented a pair of choices in 1953 that revealed a systematic pattern of preferences violating the independence axiom of expected utility theory, and this became known as the Allais paradox, one of the most influential demonstrations that human decision-making deviates from the prescriptions of standard rational choice theory. And the paradox shows that people's preferences can be influenced by irrelevant alternatives, by outcomes that occur in both options and should therefore cancel out, yet somehow affect which option is chosen. The first choice involves two lotteries. Lottery A offers a certain gain of $1 million, while Lottery B offers a 10% chance of winning $5 million, an 89% chance of winning $1 million, and a 1% chance of winning nothing. And when faced with this choice, most people prefer Lottery A, the certain million, preferring the sure thing to the gamble, even though the gamble has a higher expected value. And this preference reflects risk aversion, a common and generally accepted feature of human decision-making. The second choice involves two different lotteries. Lottery C offers an 11% chance of winning $1 million and an 89% chance of winning nothing, while Lottery D offers a 10% chance of winning $5 million and a 90% chance of winning nothing. And when faced with this choice, most people prefer Lottery D, the gamble with the higher potential payoff, accepting the slightly lower probability of winning in exchange for the much larger prize. The paradox emerges when these two preference patterns are analysed together, because the independence axiom of expected utility theory requires that if Lottery A is preferred to Lottery B, then Lottery C should be preferred to Lottery D. And the reason is that lotteries A and B differ from lotteries C and D only in that there is an 89% chance in both A and B of receiving $1 million, and in both C and D this 89% outcome is replaced with winning nothing, and this replacement should affect both lotteries equally, should not change the preference order, because the independence axiom says that preferences between lotteries should depend only on outcomes where the lotteries differ, not on outcomes that are the same in both. And the 89% probability mass is shifted in the same way for both pairs, and so if you prefer A to B, you should also prefer C to D. And if you prefer D to C, you should also prefer B to A. The typical pattern of preferences, A over B and D over C, cannot be represented by any utility function satisfying the expected utility axioms. And so the Allais paradox demonstrates that people systematically violate the independence axiom, that their preferences are sensitive to common outcomes in ways that expected utility theory does not permit. And this violation is robust, appearing in experiments with diverse populations, with real monetary stakes, with careful experimental design. And the paradox cannot be dismissed as error or confusion, but represents a genuine feature of human decision-making. The paradox has inspired alternative theories that can accommodate the observed preferences, including prospect theory, developed by Daniel Kahneman and Amos Tversky, which modifies expected utility theory by introducing reference points, by treating gains and losses differently, by allowing for probability weighting where people overweight small probabilities and underweight large probabilities. And these modifications can explain the Allais preferences, because in the first choice, the certainty of $1 million receives extra weight, making Lottery A more attractive, while in the second choice the small probabilities are overweighted, making the 10% chance of $5 million in Lottery D seem more appealing than the 11% chance of $1 million in Lottery C. Other theories include regret theory, where people anticipate the regret they would feel if they made the wrong choice. And this anticipated regret influences preferences in ways that violate independence, because the certain million in Lottery A avoids the regret of choosing the gamble and losing everything, while the choices between C and D do not have this asymmetry. And rank-dependent utility theory, which generalizes expected utility by allowing the utility of lotteries to depend not just on outcomes and probabilities, but on the rank ordering of outcomes, and this allows for preferences that violate independence while maintaining other desirable properties. The Allais paradox raises normative questions about rationality. Some argue that the independence axiom is a fundamental requirement of rational choice, that violating it leads to incoherence, to preferences that can be exploited through Dutch books or money pumps, to decision-making that is systematically suboptimal, and that people who exhibit Allais preferences are making mistakes and should revise their preferences to conform to expected utility theory. While others argue that the independence axiom, while mathematically convenient, is not a necessary condition for rationality, that it does not capture important aspects of how people value uncertain prospects, that preferences like those in the Allais paradox reflect legitimate concerns about certainty, regret, and the context of choice, and that we should revise our normative theories to accommodate these preferences rather than dismissing them as irrational. The paradox also has practical implications for economics and policy, because if people systematically violate independence, then markets may not function as standard theory predicts. Risk preferences may be context-dependent. Insurance and investment decisions may be influenced by framing effects, and policies designed to maximize expected utility may not align with what people actually prefer. And understanding these deviations from expected utility helps explain phenomena like the equity premium puzzle, the disposition effect, and other anomalies in financial markets and economic behavior. The lotteries sit before you, the choices must be made, and your preferences, revealed through your choices, tell a story about how you value certainty and risk, about how you weigh probabilities and outcomes, and the story violates the axioms of rational choice, violates the clean mathematical structure of expected utility theory, and yet the choices feel reasonable, feel justified, feel like they reflect something important about value and uncertainty that the theory misses, and the paradox persists. The gap between theory and behavior remains. The independence axiom is violated again and again in experiments and in life, and decision theorists must choose. Either insist that the axiom is normatively binding and that violators are irrational, or acknowledge that the axiom is too strong, that rational choice is more complex than expected utility allows, and that new theories are needed to capture the richness of human decision-making. And the Allais paradox remains a landmark, a decisive demonstration that classical rational choice theory does not fully describe or prescribe human behavior, a challenge that spawned new theories and new research programs, and a reminder that rationality is contested, that what counts as a reasonable choice depends on assumptions and frameworks that are themselves open to question, and the lotteries remain, the choices remain, the preferences remain, and the paradox endures, unsolved in the sense that no consensus has emerged about whether the preferences are rational or irrational, about whether we should revise our theories or our preferences, about whether independence is a negotiable axiom or a non-negotiable requirement. And the debate continues. Philosophers and economists and psychologists arguing about what rationality requires, about what humans actually do, and about the relationship between these two questions. Schrödinger's cat, the pet that's both alive and dead. A cat sits in a sealed box, a box that cannot be opened or observed from the outside. And inside the box with the cat is a device, a quantum mechanism that has a 50% chance of killing the cat within 1 hour and a 50% chance of leaving the cat alive. Perhaps a vial of poison that will break if a single radioactive atom decays. And the decay is a quantum event, genuinely random, with no way to predict whether it will happen in the next hour. And so after 1 hour has passed, the cat is either alive or dead. 50-50 odds. And this seems straightforward, but the paradox emerges when quantum mechanics is taken seriously, when the rules of quantum theory are applied consistently, because quantum mechanics says that before a measurement is made, before the box is opened and the cat is observed, the system exists in a superposition, a combination of both possible states simultaneously. And so the cat is both alive and dead at the same time, existing in a strange limbo where neither state is definite until observation collapses. The superposition and forces the system into one state or the other. And this is Schrödinger's cat, a thought experiment devised by physicist Erwin Schrödinger in 1935 to illustrate what he saw as the absurdity of applying quantum mechanics to macroscopic objects to show that something was wrong with the standard interpretation of quantum theory. Imagine the situation step by step. At the beginning, the cat is alive, the radioactive atom has not yet decayed, and the quantum state is well defined. But as time passes, the atom enters a superposition of decayed and not decayed, because quantum mechanics describes it with a wave function that assigns amplitudes to both possibilities, and these amplitudes evolve smoothly, and the atom is in a state of quantum indeterminacy, neither definitely decayed nor definitely not decayed until a measurement is made. And this indeterminacy is not ignorance, not a matter of the atom being in one state or the other, and we just do not know which, but a genuine feature of quantum reality. The atom literally does not have a definite state until measured. And because the poison release is coupled to the atom's state, the poison is both released and not released. And the cat is both dead and alive, existing in a superposition of macroscopic states. And this conclusion seems absurd, seems to violate everything we know about cats and boxes and life and death. And Schrödinger intended it to be absurd, to show that something must be wrong with the orthodox interpretation of quantum mechanics, that the theory cannot be applied consistently to large objects, that there must be a boundary somewhere between the quantum realm where superpositions occur and the classical realm where objects have definite states. The paradox has generated an enormous amount of discussion and debate in physics and philosophy, with different interpretations of quantum mechanics offering different resolutions. The Copenhagen interpretation, the dominant view in Schrödinger's time, says that the wave function collapses upon measurement, that the act of observation forces the system into one definite state. And so when the box is opened and the cat is observed, the superposition collapses and the cat becomes definitely alive or definitely dead. But this raises questions about what counts as a measurement, about what constitutes an observer, about whether consciousness is required to collapse the wave function, or whether any physical interaction suffices. And these questions remain controversial, and the Copenhagen interpretation does not provide clear answers, does not specify where the quantum classical boundary lies. The many worlds interpretation offers a different resolution, saying that the wave function never collapses, that both outcomes occur, that the universe splits into two branches, one where the cat is alive and one where the cat is dead, and both branches are equally real, and the observer also splits, becoming two versions, one observing a live cat and one observing a dead cat, and each version believes they have observed a definite outcome. But from a global perspective, both outcomes happen, and the superposition is resolved not by collapse but by branching. And this interpretation avoids the measurement problem, avoids the need to specify what counts as a measurement. But it introduces other difficulties: the proliferation of parallel worlds, the question of what it means for both outcomes to be real, and whether this is a genuine solution or merely a reformulation of the problem. Decoherence theory provides another perspective, focusing on the interaction between the quantum system and its environment. and it shows that macroscopic objects, like cats, are constantly interacting with their surroundings, with air molecules, with photons, with thermal radiation, and these interactions cause the quantum coherence, the delicate phase relationships that allow superpositions to be destroyed very rapidly in a fraction of a second for macroscopic objects. And once coherence is lost, the system behaves classically, appears to be in one definite state, and so the cat never actually exists in a superposition of alive and dead, or exists in such a state for only an immeasurably short time before decoherence converts it to a classical mixture, a probabilistic state where the cat is either alive or dead. We just do not know which until we look. And this dissolves the paradox by denying that macroscopic superpositions persist long enough to be observable. The paradox also raises questions about the role of consciousness in quantum mechanics, about whether an observer must be conscious to collapse the wave function, and some interpretations suggest that consciousness plays a special role, that the cat remains in superposition until a conscious being opens the box and perceives the outcome. And this view has been criticized as mystical, as importing mind into physics in ways that are unnecessary and unhelpful, and most physicists reject it, preferring interpretations that treat measurement as a physical process involving interactions with macroscopic devices, not requiring consciousness. But the question remains open, debated, unresolved, and Schrödinger's cat sits at the center of this debate, a symbol of the deep puzzles that quantum mechanics presents. Visualize the box, sealed and opaque, and inside the cat waits, and the quantum device ticks, and the atom hovers in superposition. And according to quantum mechanics, the entire contents of the box, the atom, the device, the poison, the cat, all exist in a superposition of two macroscopically distinct states: alive, cat no decay, and dead cat decay. And this superposition is described by a wave function that smoothly evolves, and the two branches of the wave function correspond to two different realities. And yet before the box is opened, there is only one box, one cat, one system. And the paradox is that quantum mechanics seems to say the cat is both alive and dead. While common sense says the cat is either alive or dead, we just do not know which, and this clash between quantum formalism and classical intuition is the heart of Schrödinger's cat, a paradox that has no agreed-upon solution, that different interpretations resolve in different ways, and that continues to drive research in the foundations of quantum mechanics, in efforts to understand what measurement means, what quantum states represent, and how the quantum world relates to the classical world we experience. The box sits on the table, the hour passes, and the cat's fate is sealed. Or is it? Or is the cat in limbo, suspended between life and death, waiting for observation to make reality definite? And the paradox endures, not because physicists do not understand quantum mechanics, but because quantum mechanics, understood correctly, leads to conclusions that seem impossible, that violate everyday experience, that force choices between interpretations that are empirically equivalent but conceptually divergent. And Schrödinger's cat remains the most famous illustration of this strangeness, a thought experiment that has entered popular culture, a paradox that symbolizes the weirdness of quantum reality. And the cat, alive and dead, real and hypothetical, continues to haunt physics and philosophy, a permanent reminder that the quantum world is not merely different in degree from the classical world, but different in kind, governed by rules that defy visualization and resist intuitive understanding. And the paradox persists, unresolved in the deepest sense, a puzzle that reveals the limits of human intuition and the challenge of making sense of a theory that works perfectly in practice but remains mysterious in principle. The binding problem: how your brain unites what it processes separately. A neuroscientist examines how the brain processes visual information, discovers that different features of objects are processed in different brain regions. Color is processed in one area, motion in another, shape in a third, orientation in a fourth, And all these features are analysed separately, by specialised modules, by distinct populations of neurons. And yet when you look at a red ball moving to the right, you do not experience colour, motion and shape as separate. Do not see redness here and roundness there and rightward motion elsewhere, but see a unified object, a red round ball moving right, and all the features are bound together, are experienced as properties of a single thing. And this creates the binding problem, the puzzle of how the brain, which processes features separately, creates unified conscious experiences, how separate neural processes give rise to integrated perception, how the many become one. And this problem is fundamental, touches on the nature of consciousness, on how neural activity becomes experience, on what unifies experience into coherent wholes, and no complete solution exists. Various theories have been proposed, but the binding problem remains one of the deep mysteries of neuroscience, a gap between our understanding of neural processing and our understanding of consciousness. Imagine the visual system as a factory, with different departments processing different aspects of the product. One department handles colour, another handles shape, another handles location, and all work in parallel, all process simultaneously, and each department produces its output colour information, shape information, location information, and somehow these separate outputs must be combined, must be integrated into a unified representation, must be bound together so that you experience a red ball rather than redness and roundness as separate unlocalized features. And the binding problem asks how this combination occurs. What mechanism ensures that the right features are bound together, that the redness is attributed to the round object and not to the square object that happens to be present in the scene. And this correct attribution, this accurate binding, is critical for coherent perception, for navigating the world successfully, and yet how the brain achieves it remains unclear. The binding problem has two aspects: the feature binding problem, which asks how different features of the same object are bound together, and the object binding problem, which asks how different objects are kept separate, are not confused with each other, and both aspects are challenging. Both reveal that perceptual unity is not given automatically by neural processing, but requires some mechanism, some process that groups features appropriately, and various mechanisms have been proposed. Attention has been suggested as a solution. The idea that attention binds features, that attended objects have their features integrated, while unattended objects do not. And this explains why feature binding errors occur when attention is diverted, why illusory conjunctions occur where features from different objects are misbound, are attributed incorrectly. Visualize attention as a spotlight that illuminates objects one at a time, and within the spotlight features are bound, are integrated, and outside the spotlight features remain separate, are not integrated. And this attentional binding theory has some support, has experimental evidence showing that feature binding requires attention, that without attention, features can be perceived separately without being bound correctly, and illusory conjunctions are more common under conditions of inattention, supporting the idea that attention is necessary for binding. But attention cannot be the complete solution, because some binding occurs pre-attentively. Some feature integration happens automatically before attention is applied, and so attention is part of the story, but not the whole story. Another proposed mechanism is temporal synchrony, the idea that neurons representing features of the same object fire in synchrony, fire together, and this synchrony is the binding code, is what marks features as belonging together and neurons representing different objects, fire at different times or with different phases, and this temporal separation keeps objects distinct, prevents their features from being bound together. And this synchrony theory has been influential, has generated extensive research, has led to discovery of synchronized neural oscillations in visual cortex, but the theory faces challenges. It is not clear that synchrony is sufficient for binding, it is not clear that consciousness depends on synchrony, and some experiments have failed to find the predicted correlations between synchrony and perceptual binding, and the theory remains controversial. A third approach argues that binding occurs through convergence, through hierarchical processing, where features are combined in higher-level areas, and early visual areas process features separately, but project to higher areas that represent combinations, that have neurons responding to specific conjunctions of features. And these conjunction neurons represent bound objects, represent integrated wholes. And binding is achieved through this hierarchical architecture, through neurons that explicitly encode feature combinations. And this approach has support from single neuron recordings, showing that higher visual areas have neurons with complex selectivity, neurons that respond to specific combinations of shape and color and motion. And these neurons could be the neural basis of bound object representations. The binding problem also connects to consciousness, because unified conscious experience seems to require binding, seems to require that separate neural processes be integrated into coherent wholes, and some theories of consciousness, like integrated information theory, make integration central, argue that consciousness arises from integrated information, from systems where different parts interact and constrain each other, and binding as a form of integration is the combination of separately processed features into unified representations. And understanding binding may be crucial for understanding consciousness, may reveal how neural processes give rise to unified experience. The problem also has practical implications for understanding neurological conditions where binding fails, where patients see features but cannot bind them correctly, and such conditions exist. Barlin's syndrome is one example, where patients can see individual features but cannot perceive objects, cannot integrate features into wholes. And these patients provide evidence that binding is a genuine process, is not automatic, can be disrupted by brain damage. And studying these patients helps understand normal binding, helps identify the brain regions and processes necessary for feature integration. Some philosophers argue that the binding problem is really a problem about consciousness, about how physical processes give rise to subjective experience, about the hard problem. And binding is one aspect of this, is the problem of how separate neural processes give rise to unified conscious experiences. And solving the binding problem may require solving the hard problem, may require understanding how neural activity becomes experience. And this makes binding one of the deepest problems in neuroscience, a problem at the interface between neuroscience and philosophy of mind. The brain processes features separately, color here, motion there, shape elsewhere, and yet you see unified objects, see red round balls moving, see integrated wholes, and how this integration occurs, how the separate processes give rise to unified experiences, remains one of the great unsolved problems. The binding problem stands, challenging, fundamental, revealing a gap between our understanding of neural processing and our understanding of perception. And various theories exist, various mechanisms have been proposed. Attention, synchrony, convergence, but no theory is complete. No theory explains all aspects of binding, and the problem persists as one of neuroscience's deepest mysteries. A puzzle about how unity emerges from multiplicity, how the brain binds what it processes separately, and the question remains open. The mechanism remains elusive, and the binding problem endures. Quine's Gavagai problem? Why we can never know what anyone really means. An anthropologist arrives in a remote village to study an unknown language, a language no outsider has encountered before. And the anthropologist has no translator, no dictionary, no common linguistic framework, only observations and patience, and the method is radical translation. Learning the language from scratch by observing how natives use words in response to events. And one day, a rabbit runs past and a native points and says Gavagai, and the anthropologist writes in the notebook, Gavagai means rabbit. And this seems reasonable. seems like an obvious inference. The native saw a rabbit and said gavagai, so gavagai must refer to rabbits. But philosopher Willard Van Orman Quine points out a deep problem about meaning and translation. Because gavagai might mean rabbit, but it might also mean undetached rabbit part, or rabbit stage, or collection of rabbit molecules, or instance of rabbithood. And all these translations are consistent with the native's behaviour. All would lead the native to say gavagai in exactly the same circumstances, whenever a rabbit is present, and there is no fact of the matter, no objective truth about which translation is correct, no way to determine what gavagai really means. And this indeterminacy is not due to practical limitations, not due to insufficient evidence, but is fundamental, is a consequence of how meaning works. And this is Quine's gavagai problem, also called the problem of indeterminacy of translation, a challenge to the idea that words have determinate meanings, that translation has right answers, and that we can know what others mean when they speak. Imagine trying to distinguish between gavagai means rabbit and gavagai means undetached rabbit part. And you point to the rabbit and the native says gavagai, and you point to the rabbit's ear and ask whether this is gavagai, and the native responds, but you do not know whether the response means yes because the ear is an undetached rabbit part, or no, because the ear is not a whole rabbit, or something else entirely. And every test you design, every question you ask, can be interpreted in multiple ways, can be answered consistently by multiple translations, and no amount of observation, no behavioural evidence can definitively settle which translation is correct, because the native's behaviour under all possible circumstances is compatible with multiple interpretations. And Quine argues that this shows meaning is indeterminate, that there is no fact about what gavagai really means, only different translation manuals that work equally well, that map the native's language onto ours in different but equally legitimate ways. The problem generalizes beyond anthropology to all understanding of language, because even when we share a language, even when we both speak English, the gavagai problem applies. We cannot be certain that we mean the same thing by our words, that rabbit means to you what it means to me. We might be using different concepts, carved up differently, but our behavior is similar enough that we never notice the difference. And this raises the disturbing possibility that communication is always partial, always approximate, that we never fully understand each other, that meaning is not something objective that words have, but something we impose through interpretation, and different interpretations can fit the evidence equally well, and there is no transcendent perspective from which to judge which interpretation is correct. Visualize meaning as a relationship between words and world, and Quine's point is that this relationship is underdetermined by behaviour, by the evidence available to translators, because infinitely many relationships are consistent with the same behavioural evidence. Infinitely many ways of mapping words to world produce the same observable patterns, and choosing among these possibilities requires going beyond evidence, requires making decisions that are not forced by facts, and these decisions constitute meaning rather than discovering it. And so meaning is partially conventional, partially stipulated, not fully determined by reality. The gavagai problem challenges referential theories of meaning, theories that say words mean things because they refer to objects in the world, because rabbit refers to rabbits, and water refers to water, and Quine's argument shows that reference is inscrutable, cannot be determined from behaviour alone, because words can be interpreted as referring to different things, different ways of carving up reality, and all interpretations fit the evidence, and so reference is not an objective relation, but is relative to a translation manual, relative to a scheme of interpretation, and different manuals. Different schemes can assign different references to the same words while remaining equally correct. One response to the gavagai problem accepts the indeterminacy, embraces it as a truth about meaning, argues that Quine is right, that there is no fact of the matter about what words mean beyond what is determined by behavioral evidence and meaning is holistic depends on the entire network of beliefs and language practices. And translation manuals are theoretical frameworks that organize this evidence. And like all theories, they are underdetermined by data, and multiple theories fit the same data equally well. And choosing among them involves pragmatic considerations, simplicity, utility, coherence, but not truth in any absolute sense. And this response treats meaning as a human construction, something we create through practices rather than something we discover in nature. Another response denies the indeterminacy, argues that Quine's thought experiment is artificial, that in real translation situations additional evidence is available, evidence about intentions, about how speakers correct each other, about the structure of their conceptual schemes. And this additional evidence narrows down the possibilities, rules out bizarre interpretations like undetached rabbit part, and determines that gavagai means rabbit in the ordinary sense. And while perfect certainty may be impossible, practical determinacy is achievable, and meaning is objective enough for communication to succeed, for translation to have right and wrong answers. And the gavagai problem is an epistemological worry, a concern about how we know what words mean. But it does not show that words lack determinate meanings, only that discovering those meanings is difficult. A third response appeals to charity, to the principle that we should interpret speakers as making sense, as having coherent beliefs, as speaking truly most of the time. And this principle constrains translation, rules out interpretations that make speakers irrational or massively mistaken. And while charity does not uniquely determine translation, it narrows the range of acceptable interpretations, and combined with simplicity and other pragmatic virtues, it makes translation tractable, makes it possible to arrive at good translations, even if not perfect ones. And this response treats translation as an interpretive practice, guided by norms rather than as a purely empirical investigation, guided only by behavior. The gavagai problem also connects to broader philosophical issues about realism and anti-realism, about whether there are objective facts independent of our theories and languages. Because if meaning is indeterminate, then perhaps reality itself is indeterminate. Perhaps there is no fact about whether rabbits or undetached rabbit parts exist, only different ways of organizing experience, different conceptual schemes that carve up the world differently. And Quine's ontological relativity, his claim that what objects exist is relative to a language or theory, follows from the gavagai problem, from the recognition that reference is inscrutable, that we cannot say what exists absolutely, but only what exists relative to a framework. The anthropologist sits with a notebook, the word gavagai recorded, the translation uncertain, and the native speaks, and the anthropologist interprets, and communication proceeds approximately, pragmatically, successfully enough for practical purposes, and whether gavagai really means rabbit or something else remains undetermined, remains a question without an answer. And Quine's problem persists, not as a practical obstacle to translation, but as a philosophical challenge to theories of meaning, as a demonstration that meaning is more elusive than we thought, more dependent on interpretation and less determined by facts. And the gavagai problem endures as one of Quine's most influential contributions, a thought experiment that changed how philosophers think about language, about meaning, about translation, and about the relationship between words and world. And the problem remains unsolved, perhaps unsolvable, a permanent feature of linguistic philosophy, a reminder that understanding each other is harder than it seems, that meaning is indeterminate, that communication is an achievement rather than an automatic consequence of shared language, and that the gap between what we say and what we mean, between our words and their reference, can never be fully closed. And the rabbit runs past and the native says, gavagai, and we translate approximately, hopefully, never quite certain that we have understood. The Achilles and the tortoise. Achilles, the swift-footed hero of Greek legend, agrees to race a tortoise, and to make the contest fair, the tortoise is given a head start. Perhaps 100 meters, and the race begins, and Achilles runs swiftly toward the point where the tortoise started. But by the time he reaches that point, the tortoise has moved forward a small distance, perhaps 10 meters, and so Achilles runs toward that new position. But again, by the time he arrives, the tortoise has advanced a bit further, perhaps 1 meter, and this process continues. Each time Achilles reaches where the tortoise was, the tortoise has moved ahead. And it seems that Achilles can never quite catch up, never quite overtake the slower creature. And yet common sense insists that, of course, Achilles will pass the tortoise. That speed wins races, that the faster runner always overtakes the slower, given enough time and distance. And this contradiction between logic and intuition is Zeno's most famous paradox, a puzzle that has captivated philosophers and mathematicians for over 2 millennia. Zeno of Elea constructed this argument in the 5th century BCE as part of his defense of Parmenidean monism, the idea that reality is one unchanging whole and that motion and plurality are illusions. And the paradox was meant to show that the concept of motion leads to absurdity, that if we accept that space and time can be divided infinitely, then the faster can never overtake the slower. And since this conclusion is obviously false, something must be wrong with our assumptions about motion and change. The paradox rests on the idea that Achilles must complete infinitely many tasks, reaching the first point where the tortoise was, then the second, then the third, and so on without end. And if each task takes some amount of time, however small, then infinitely many tasks would require infinite time. And yet in reality, Achilles catches and passes the tortoise in a finite time. And so where is the error? Aristotle argued that the paradox confuses potential and actual infinity, that while the path can be divided into infinitely many segments in thought, Achilles does not actually perform infinitely many separate actions. He simply runs, continuously and smoothly. And the infinite division is an artifact of analysis, not a feature of the motion itself. The resolution became clearer with the development of calculus, which showed that an infinite series of diminishing intervals can sum to a finite total, that 1 + 1/10 + 100th, and so on converges to a specific finite value. And so the infinite number of time intervals Achilles requires to reach each successive position also sum to a finite time, the time it takes him to overtake the tortoise. Yet the paradox retains a strange power, a sense that something about infinity remains counterintuitive, that the idea of completing an infinite number of steps feels impossible, even when mathematics insists it is not, and philosophers continue to debate whether the mathematical resolution truly captures the conceptual problem or merely sidesteps it. The paradox also connects to questions about the nature of space and time, whether they are continuous or discrete, whether motion is genuinely smooth or composed of tiny jumps, whether there is a smallest possible distance or duration beyond which reality cannot be divided. And these questions remain open in modern physics, where quantum mechanics and theories of spacetime suggest that the classical picture of smooth continuous motion may break down at the smallest scales. If you enjoy these explorations of paradox and the limits of thought, consider subscribing so you never miss a journey into philosophy's most perplexing puzzles, and perhaps leave a comment sharing where you are in the world as you listen to these ideas unfold. Achilles and the tortoise remain locked in their eternal race, a metaphor for the human attempt to reconcile the finite with the infinite, the continuous with the discrete, the logical with the intuitive. And the paradox endures as a reminder that even the simplest motion, a hero chasing a tortoise, conceals within it mysteries that have not been fully solved. Questions that linger at the boundary where mathematics meets reality, where reason meets experience, where what must be true, according to logic, clashes with what obviously is true, according to the world. The boy or girl paradox. A family has two children, and you're told that at least one of them is a boy, and the question is posed, what is the probability that both children are boys? And the intuitive answer is 1/2, because the other child is either a boy or a girl with equal probability, but this reasoning is incorrect. The actual probability is 1/3, and this is the boy or girl paradox, a puzzle in conditional probability that has generated confusion and debate for decades, with different versions yielding different answers depending on exactly how the information is obtained and what assumptions are made about the selection process. The solution proceeds by considering all possible, equally likely combinations of two children. There are 4 possibilities: boy-boy, boy-girl, girl-boy, girl-girl, and girl-girl, where the order matters because the first child and second child are distinct, even if both are boys or both are girls. And if we are told that at least one child is a boy, then the girl-girl possibility is eliminated, leaving 3 equally likely cases: boy-boy, boy-girl, and girl-boy. And only in one of these 3 cases are both children boys, and so the probability is 1/3, not 1/2. The paradox arises because the conditioning statement, at least one is a boy, is not the same as knowing the gender of a specific child. If instead we are told that the older child is a boy, or the younger child is a boy, then the probability that both are boys becomes 1/2, because we are conditioning on a specific child being a boy rather than on the existential claim that at least one child somewhere in the family is a boy. And this distinction, subtle as it seems, makes a crucial difference to the probability calculation. The boy or girl paradox has many variations that probe the boundaries of the problem and reveal how sensitive the answer is to the exact specification of the scenario. One famous variant involves meeting a man who says he has 2 children, and one of them is a boy named Tuesday, meaning the boy was born on a Tuesday, and this additional information about the day of the week changes the probabilities in a surprising way, because it reduces the number of scenarios consistent with the statement, and the probability that both children are boys increases from 1/3 to 13/27. And this result seems bizarre, seems like the day of the week should be irrelevant, but the mathematics is sound. The additional specificity affects the conditional probabilities. Another variation asks, what if you meet a man with 2 children, and you see one of them, a boy? Does this change the answer? And the answer is yes. Seeing a specific boy is different from being told that at least one child is a boy, because seeing introduces selection effects. You are more likely to see a boy in families with 2 boys than in families with 1 boy, and so the probability calculation must account for the process by which the information was obtained, and different processes lead to different answers. And this sensitivity to selection effects is a general feature of conditional probability problems, and it explains why the boy or girl paradox has multiple defensible answers depending on the scenario. The paradox connects to the reference class problem and to debates about the principle of indifference, because applying the principle of indifference requires specifying a reference class, a set of equally likely outcomes, and different choices of reference class lead to different probability assignments. And in the boy or girl paradox, the reference class could be families with at least 1 boy, or it could be situations where someone tells you that at least one child is a boy. And these are different reference classes with different probabilities. And there is no neutral or obvious way to choose between them without more information about how the scenario is set up. The paradox also raises questions about the interpretation of probability statements in natural language, because phrases like "at least one is a boy" can be interpreted in different ways, as a statement about the existence of a boy in the family, as a statement about what someone knows or has observed, or as a statement about what information has been communicated, and each interpretation leads to different formal models and different probability calculations. And this ambiguity in natural language is a source of many probability paradoxes, where the mathematical answer depends on details that are not fully specified in the informal statement of the problem. Bayesian statisticians and frequentists also interpret the paradox differently. Bayesians treat probability as degrees of belief and calculate conditional probabilities using Bayes' theorem, while frequentists treat probability as long-run frequencies and may question whether the conditional probability is well defined without specifying a clear sampling procedure. And these different philosophical approaches to probability lead to different emphases in how the paradox is understood and resolved, though both traditions agree on the mathematical calculations once the problem is precisely formulated. The boy or girl paradox has practical analogues in genetics and medicine, where the probability of certain conditions depends on family history in ways that are similar to the structure of the paradox. For instance, the probability that a family carries a recessive genetic trait depends on how many children are observed to have the trait, and the calculations must account for ascertainment bias, the fact that families are more likely to come to medical attention if they have affected children, and this bias affects the probability assessments in ways that parallel the selection effects in the boy or girl paradox. The family walks down the street, 2 children beside them, and you know that at least one is a boy, and the question remains, what is the probability that both are boys? And the answer depends on how you came to know this fact, on whether you asked about a specific child or about any child, on whether you saw a boy or were merely told that at least one exists, and each variation of the scenario changes the answer, shifts the probabilities, reveals that conditional probability is sensitive to context, to process, to the mechanisms by which information is acquired and communicated, and the paradox persists as a puzzle, as a teaching tool, as a demonstration of how subtle probability can be, how carefully problems must be formulated, how easily intuition can mislead. And the boy walks ahead, evidence of his existence, shifting probabilities, conditioning beliefs, and the mathematics unfolds, precise and unforgiving, calculating 1/3 or 1/2 or 13/27, depending on the details, and the intuition struggles to keep up, struggles to grasp why the day of the week matters, why seeing is different from being told, why reference classes and selection effects have such profound impacts on what should be simple questions, and the paradox endures, unsettled in the sense that people continue to disagree about which answer is correct for which version, continue to debate whether the problem is well posed, continue to find new variations that test the boundaries of conditional probability, and the family continues walking. The boy or boys or boy and girl continue existing, and the question remains open, answerable only when the scenario is specified with enough precision to eliminate ambiguity, to fix the reference class, to determine the selection process, and until then, the paradox lives on. A reminder that probability is not just mathematics, but interpretation. Not just calculation, but careful attention to how information is obtained, how questions are asked, and how evidence is generated. The barber paradox. In a small village, there lives a barber who follows a single rule. He shaves all and only those men in the village who do not shave themselves. And this rule seems simple enough until the question emerges. Does the barber shave himself? And suddenly the logic collapses into contradiction. If the barber shaves himself, then he belongs to the group of men who shave themselves, which means according to the rule, he should not shave himself because he only shaves men who do not shave themselves. But if he does not shave himself, then he belongs to the group of men who do not shave themselves, which means, according to the rule, he must shave himself because he shaves all men who do not shave themselves, and the loop tightens without escape, spinning endlessly between two impossible options. Bertrand Russell popularized this version of his own paradox as a way to make the abstract problem of self-referential sets more accessible, more human, more vivid, because a barber is easier to imagine than a set of all sets that do not contain themselves. Yet the logical structure remains identical, a rule that turns inward and devours its own coherence. The paradox reveals something unsettling about definitions and categories, that not all rules can be consistently applied, that language and logic can conspire to create situations that seem perfectly reasonable until examined closely, and then they shatter. Some philosophers argue that the barber simply cannot exist, that the rule itself is contradictory, and therefore no such barber could ever follow it in reality, while others suggest that the problem lies in assuming the rule must apply universally, that perhaps the barber is exempt from his own rule, or that the village contains no barber at all. The paradox also exposes the danger of self-reference, the way that statements or rules that loop back on themselves can generate infinite regress or outright contradiction. And this has implications far beyond barbershops, touching mathematics, computer science, law, and any system that attempts to regulate itself from within. In set theory, the barber paradox mirrors Russell's discovery that naive set theory permits the construction of sets that cannot exist without contradiction, forcing mathematicians to impose restrictions on which sets are allowed to form, creating hierarchies and boundaries to prevent self-reference from poisoning the system. The barber stands at the edge of reason, a figure trapped in a loop of his own making, unable to shave or not shave without violating the very rule that defines his existence, and in this way, he becomes a symbol of the limits of logic, a reminder that not every question has an answer, that some problems resist resolution no matter how carefully they are examined. The paradox lingers in the mind, a simple story about a man and a razor that somehow reveals a crack in the foundation of thought itself, and once noticed, it cannot be ignored, appearing again and again wherever rules turn inward, wherever systems attempt to contain themselves, wherever language reaches the boundary of what it can coherently express. The Banach-Tarski paradox. A solid sphere can be decomposed into a finite number of pieces, which can then be reassembled using only rotations and translations to form two solid spheres, each identical to the original. And this seems to violate conservation of volume, seems to create matter from nothing, seems to be impossible, and yet it is a theorem in mathematics, proven rigorously using the axiom of choice and the properties of infinite point sets. And this is the Banach-Tarski paradox, named after Stefan Banach and Alfred Tarski, who proved it in 1924. And the paradox reveals deep and counterintuitive features of infinite decompositions, of non-measurable sets, and of the relationship between mathematics and physical reality. The proof proceeds by decomposing the sphere into a finite number of pieces, typically 5 or 6, and each piece is a set of points, not a solid region with smooth boundaries, but a scattered, disconnected, infinitely complex collection of points. And these pieces are non-measurable, meaning they do not have well-defined volumes in the usual sense. They cannot be assigned a size using standard measure theory, and this is crucial because measurable sets cannot be duplicated. Conservation of volume holds for measurable sets, but non-measurable sets escape this constraint. They can be rearranged in ways that seem to violate intuition, and the Banach-Tarski paradox exploits this by constructing pieces that are so pathological, so wildly scattered, that they can be rotated and translated to form two complete spheres. The decomposition uses the axiom of choice, the principle that given any collection of non-empty sets, there exists a way to choose one element from each set, and the axiom of choice is independent of the other axioms of set theory. It cannot be proven or disproven from the standard axioms, and some mathematicians reject it precisely because it leads to results, like the Banach-Tarski paradox, results that seem absurd, and rejecting the axiom of choice avoids the paradox. But it also cripples large parts of modern mathematics. Many important theorems depend on the axiom of choice, and most mathematicians accept it despite its counterintuitive consequences. The paradox applies only to objects in three-dimensional space, or higher. It does not work in two dimensions. A disk cannot be decomposed and reassembled into two disks. And this is because the group of rotations in the plane is amenable, meaning it admits a certain kind of averaging that prevents paradoxical decompositions, while the group of rotations in three-dimensional space is non-amenable, and this non-amenability is what makes the Banach-Tarski paradox possible. The fact that rotations in three dimensions can be combined in ways that allow pieces to be moved around and duplicated. The paradox raises questions about the relationship between mathematical objects and physical objects, because while the Banach-Tarski theorem is mathematically rigorous, it does not imply that a physical sphere can be duplicated. The decomposition involves infinitely complex sets, pieces that are not solid regions but scattered collections of points, with no smooth boundaries, and such pieces cannot be physically realized, cannot be cut or manipulated, and so the paradox is a feature of mathematical idealizations rather than a claim about physical reality. And this distinction is important. The paradox shows that mathematical spheres treated as sets of points behave in strange ways, but it does not threaten conservation of mass or energy in physics, because physical objects are not sets of points but arrangements of atoms or fields or quantum states, and these are governed by physical laws that do not permit paradoxical duplication. Some mathematicians and philosophers argue that the Banach-Tarski paradox is not really a paradox but a theorem, a surprising result that reveals features of infinite point sets and non-measurable sets, and that calling it a paradox is misleading, suggesting contradiction when there is none, only counterintuitive behavior. And from this perspective, the paradox is valuable precisely because it challenges intuition, because it shows that infinite collections have properties that finite collections lack, that measure theory has limits, that the axiom of choice has strange consequences, and that mathematics is richer and stranger than naive expectations suggest. Others find the paradox troubling, a sign that something is wrong with the foundations, that the axiom of choice should be rejected or restricted, that non-measurable sets are pathological objects that should not be admitted into mathematics, and that theories which avoid such sets, like those based on constructive or intuitionistic logic, provide better foundations. And this debate reflects deeper disagreements about the nature of mathematical existence, about what kinds of objects mathematics should study, and about the role of intuition in guiding mathematical practice. The Banach-Tarski paradox also appears in discussions of probability and decision theory, because if a sphere can be decomposed into non-measurable pieces, then probability distributions on spheres must be carefully defined to avoid assigning probabilities to non-measurable sets. And this technical requirement reflects the same underlying issue, that not all collections of points can be measured, that probability requires measurability, and that attempting to assign probabilities to arbitrary sets leads to contradictions or paradoxes. The sphere sits on the table, solid and indivisible to the eye, but mathematically it is a set of infinitely many points. And the Banach-Tarski theorem says that these points can be partitioned into pieces, 5 or 6 strange scattered collections, and these pieces can be moved, rotated and translated and reassembled into 2 spheres, identical to the original. And the volume has doubled, or seems to have doubled, but the pieces never had well-defined volumes. They were never measurable, and so nothing has been created, no conservation law has been violated, only the intuition that decomposition preserves size, and this intuition holds for finite decompositions, for measurable pieces, but fails for infinite non-measurable pieces, and the paradox endures, a theorem that sounds impossible, a result that challenges understanding, a demonstration that mathematics contains surprises, that infinity is stranger than imagination, that point sets behave in ways that solid objects do not, and that the axiom of choice, innocent as it seems, permits constructions that defy common sense, and the sphere duplicates, mathematically, if not physically. And the paradox remains a permanent fixture in the landscape of mathematics, a result that students encounter with disbelief, that mathematicians accept as rigorous yet counterintuitive, and that philosophers debate as revealing something deep about the nature of mathematical objects, about the limits of measure theory, about the relationship between infinite idealization and finite reality. And the sphere sits there, unchanged and yet somehow doubled, a monument to the strangeness of infinity, to the power of the axiom of choice, and to the capacity of mathematics to prove truths that seem like impossibilities. Russell's paradox. In the year 1901, a young mathematician named Bertrand Russell discovered a contradiction so profound that it shattered the foundations of mathematics and forced an entire generation of logicians to rebuild their discipline from the ground up. And this contradiction became known as Russell's paradox, a simple question about sets that revealed a fatal flaw in the way mathematicians understood collections and categories. A set is merely a collection of objects, and sets can contain anything: numbers, colours, ideas, even other sets. And at first this seems harmless enough. A set of all chairs, a set of all prime numbers, a set of all books ever written. Some sets contain themselves as members and some do not. And this too seems straightforward. A catalogue of all catalogues would include itself because it is also a catalogue, while a list of all fruit does not include itself because a list is not a fruit. Russell posed a deceptively innocent question. Consider the set of all sets that do not contain themselves. Does this set contain itself? And the mind stumbles immediately into contradiction. If the set contains itself, then by definition it should not contain itself, because the rule states it only includes sets that do not contain themselves. But if it does not contain itself, then it must include itself, because it fits the criteria perfectly. And so the paradox loops without end, a perfect logical knot that cannot be untied. This was not merely a clever riddle or a philosophical curiosity, it was a disaster for mathematics, because at the time, mathematicians believed they could organize all of mathematical knowledge using set theory, a system proposed by Georg Cantor that treated sets as the fundamental building blocks of reality. But Russell's paradox proved that naive set theory was inconsistent, that it allowed contradictions to exist within its structure, and if contradictions are permitted, then anything can be proven true or false, rendering the entire system useless. Russell himself compared the paradox to a barber in a village who shaves all and only those men who do not shave themselves. And the question arises, does the barber shave himself? And if he does, then he should not, because he only shaves men who do not shave themselves. But if he does not, then he must, because he shaves all men who do not shave themselves. And the loop tightens again. Mathematicians scrambled to patch the damage, and various solutions emerged over the following decades. Zermelo and Frankel developed a new version of set theory that imposed strict rules about which sets could exist, forbidding the kind of self-reference that allowed Russell's paradox to form, while type theory introduced hierarchies that prevented sets from containing themselves by assigning different logical levels to different kinds of objects. Others embraced paraconsistent logic, systems that allow contradictions without collapse, or rejected the entire project of grounding mathematics in set theory, seeking new foundations altogether. Russell's paradox also influenced philosophy beyond mathematics, touching on questions of language, meaning, and self-reference, revealing that not all grammatically correct statements are logically coherent, that some sentences create traps from which reason cannot escape. The paradox appears in unexpected places. In computer science, where recursive definitions can cause programs to crash, in legal systems where laws reference themselves in contradictory ways, in everyday thought whenever categories attempt to classify themselves. It stands as a reminder that even the most rigorous systems of thought contain limits, that logic itself is not immune to paradox, that the quest for certainty and completeness may be forever haunted by statements that twist back on themselves and devour their own meaning. Skolem's paradox. Set theory describes infinite sets of different sizes, and Georg Cantor proved that the real numbers are uncountably infinite, that they cannot be placed in one-to-one correspondence with the natural numbers, that there are more real numbers than natural numbers. And this is one of the foundational results of modern mathematics, a theorem that establishes a hierarchy of infinities. But Thoralf Skolem discovered a paradox, or what appears to be a paradox, that threatens this result. And the paradox is that any consistent first-order theory that has an infinite model also has a countable model, a model where the domain consists of only countably many elements. And this is the Löwenheim-Skolem theorem, and applying it to set theory yields a troubling conclusion. If set theory is consistent, then it has a countable model, a model where the universe of sets is countably infinite. And yet within this model, the axioms of set theory are satisfied, including Cantor's theorem, which proves that the real numbers are uncountable. And so we have a countable model of set theory in which there exists an uncountable set. And this seems contradictory. How can a set be uncountable if the entire universe is countable? How can there be more real numbers than natural numbers if the whole model has only countably many elements? And this is Skolem's paradox. The resolution lies in understanding the distinction between internal and external perspectives, between how things appear from inside the model and how they appear from outside. From inside the countable model of set theory, all the axioms hold. Cantor's theorem is provable. The real numbers have no enumeration within the model. No bijection between the reals and the naturals exists as far as the model is concerned. And so internally, the reals are uncountable. But from outside the model, from the perspective of someone who can see the entire structure, the model itself has only countably many elements, and there exists a bijection between the elements of the model and the natural numbers. A bijection that is not itself an element of the model, that does not correspond to any set or function within the model. And so externally, the model is countable. And this distinction between internal and external is the key to resolving the paradox. Uncountability is relative. It depends on what bijections are available, and different models have different bijections. Skolem's paradox reveals something profound about the nature of mathematical existence and the limits of first-order logic. It shows that first-order logic cannot pin down the cardinality of infinite sets, that the concept of uncountability is not absolute but relative to a model, that what counts as uncountable in one model may be countable in another, and this relativity is a consequence of the expressive limitations of first-order logic, which can only quantify over elements of the domain, not over arbitrary functions or sets of elements. And so first-order set theory cannot express the existence of a bijection between two sets in an absolute way, cannot say, in a model-independent manner, that a set is countable or uncountable. Some philosophers and logicians find this relativity troubling, a sign that first-order set theory is inadequate as a foundation for mathematics, that a stronger logic, perhaps second-order logic, which allows quantification over sets and functions, is needed to capture the intended meaning of set theoretic concepts. And in second-order logic, the Löwenheim-Skolem theorem does not hold. There are categorical characterizations of structures, including characterizations of the natural numbers and the real numbers that pin down their cardinality uniquely. And so second-order logic avoids Skolem's paradox by being more expressive, by allowing statements that distinguish countable from uncountable models. But second-order logic has its own difficulties. It lacks complete proof systems. There is no algorithmic procedure that can, in principle, prove all second-order truths. And so the gain in expressiveness comes at the cost of losing some of the nice logical properties that first-order logic enjoys. Others embrace the relativity revealed by Skolem's paradox, arguing that it shows the conventional or perspectival nature of mathematical concepts, that cardinality is not an intrinsic property of sets but a relation between sets and models, that what we call uncountable is simply a set that lacks an enumeration within a particular model, and that different models can disagree about what is countable without any of them being wrong. And this perspective aligns with a pluralistic or model-theoretic approach to mathematics, where there is no single intended model of set theory, but many models, each with its own internal structure, and what is true varies from model to model, and mathematical truth is relative to a choice of model. Scolam's paradox also connects to issues about the definiteness of the continuum, about whether the set of real numbers has a well-defined cardinality, and the continuum hypothesis, which asks whether there is a set whose cardinality is strictly between that of the natural numbers and the real numbers. And this hypothesis is independent of the standard axioms of set theory, meaning that neither the hypothesis nor its negation can be proven from the axioms. And some mathematicians interpret this independence as evidence that the cardinality of the continuum is not a definite matter of fact, but depends on additional assumptions or on the choice of model. And Scolam's paradox reinforces this interpretation by showing that even the distinction between countable and uncountable is model-dependent. The paradox remains a touchstone in the philosophy of mathematics and the foundations of logic. It illustrates the limits of first-order logic, the relativity of model-theoretic notions, and the gap between formal systems and intended interpretations. And it forces careful thinking about what it means to say that a set is countable or uncountable, about whether mathematical concepts have absolute meanings or are always relative to a framework, and about the relationship between syntactic provability and semantic truth. And the paradox has no simple resolution. Different philosophers and mathematicians draw different lessons, some seeing it as a defect of first-order logic, others as a feature revealing deep truths about the nature of infinity and cardinality. And the debate continues, with implications for how we understand the foundations of mathematics, the status of set theory, and the nature of mathematical truth. The countable model sits in logical space, containing sets and functions and real numbers, and within this model, Cantor's theorem holds. The reals are uncountable, no enumeration exists, but from outside the model, the whole structure is countable, all its elements can be listed, and the real numbers of the model, uncountable internally, are countable externally. And this doubling of perspective, this split between internal and external, is the heart of Scolam's paradox, a demonstration that perspective matters, that truth is not always absolute, that models can disagree, and that first-order logic, powerful as it is, cannot capture all the nuances of infinite cardinality. And the paradox endures, a puzzle that has shaped logic and set theory, a challenge that continues to generate discussion and debate, and a reminder that even the most basic mathematical concepts, even the notion of how many, become subtle and contested when applied to infinite collections. The bald man paradox. A man stands before a mirror, his hair full and thick, and no one would call him bald, this much is certain. And yet time passes and hairs fall, one by one, slowly at first and then with gathering speed. And the question that haunts philosophers is simple and unanswerable. At what precise moment does this man become bald, after which single hair crosses the threshold from not bald to bald? And the intuition rebels against the idea that one hair could make such a difference, that the removal of a single strand could transform a person's category, could change a truth about them in such a fundamental way. The bald man paradox is a version of the Sorites paradox, focused specifically on baldness, but illustrating the same underlying problem about vagueness, boundaries, and the limits of classification. And it asks us to consider whether baldness admits of sharp boundaries, or whether it is inherently vague, a matter of degree rather than kind. And if it is vague, then how can we use the term meaningfully? How can we say that someone is bald or not bald when there seems to be no clear line separating the two states? Imagine the process in reverse, starting with a completely bald man, hairless and smooth, and now a single hair appears on his head, and surely one hair does not make him not bald. The presence of a single hair is negligible, imperceptible to casual observation, and if one hair does not change baldness, then neither does two, and if two do not, then neither does three, and this reasoning continues, step by step, until the man has a full head of hair, and yet according to the logic he should still be bald because no single hair made the difference. And this conclusion is absurd, and so something must be wrong with the reasoning, but what? The paradox forces a choice between several uncomfortable positions. One option is to accept that there is a sharp boundary, a precise number of hairs that separates bald from not bald, perhaps 10,000 hairs or 5,000 or some other specific number, and anyone with fewer hairs than this threshold is bald, while anyone with more is not bald. And this view preserves classical logic, maintains that every statement is either true or false, that vagueness is merely epistemic, a matter of our ignorance about where the true boundary lies, but this position strikes many as implausible because it seems arbitrary. There is no principled reason why 10,000 hairs should be the cutoff rather than 10,001, and the idea that baldness depends on such a precise count feels wrong, disconnected from how we actually use the term. Another option is to reject the idea of sharp boundaries and embrace the view that baldness is genuinely vague, that there are borderline cases where it is neither determinately true nor determinately false that someone is bald, cases where the world itself does not settle the question, and this view requires abandoning or modifying classical logic, accepting that by valence, the principle that every proposition is either true or false does not hold for vague predicates, and this leads to various non-classical logical systems, three-valued logics where propositions can be true, false or indeterminate, fuzzy logics where truth comes in degrees ranging continuously from 0 to 1, supervaluationism where a statement is true if it is true on all acceptable ways of making the vague term precise, and each of these approaches has costs and benefits. Each preserves some intuitions while sacrificing others. A third option is contextualism, the view that whether someone is bald depends on the context of utterance, on the standards and purposes operative in a given conversation or situation. And in one context, a man with 5,000 hairs might count as bald, while in another context only someone with fewer than 1,000 hairs would count. And this view makes baldness relative rather than absolute. And it explains why borderline cases feel uncertain, because in borderline cases the context has not provided enough information to determine which standards apply, but contextualism faces challenges too. It must explain how context determines standards, whether there are constraints on what standards can be operative, and whether contextualism avoids the Sorites paradox or merely relocates it to the question of when contexts shift. The bald man paradox also connects to broader questions about language, reference, and the relationship between words and the world. Because if most predicates in natural language are vague, and they are, nearly every adjective and many nouns admit of borderline cases, then vagueness is not a peripheral issue, but a central feature of how we communicate, and any theory of meaning must account for it, must explain how. Vague terms can be useful and informative despite their lack of sharp boundaries, and must address whether vagueness is a feature of language, of thought, of the world, or of all three. Some philosophers argue that vagueness is purely linguistic, that the world itself is precise and determinate, but our words are blunt instruments that fail to carve reality at its joints, while others suggest that vagueness exists in thought as well, that our concepts are themselves fuzzy, and still others propose that the world itself contains vague objects and properties, that reality does not always come with sharp boundaries, that nature is continuous and gradual in ways that resist precise classification. The paradox has practical implications as well. In law, where terms like reasonable and substantial and significant must be applied to real cases despite their vagueness. In medicine, where diagnostic criteria often involve thresholds that are somewhat arbitrary. In ethics, where drawing lines between permissible and impermissible actions may require confronting borderline cases where intuition provides no clear guidance. And in each of these domains, the bald man paradox is not merely an abstract puzzle, but a genuine obstacle to clear thinking and fair judgment. The paradox also raises questions about personal identity and change over time. Because if baldness is gradual, then so are many other properties: aging, growing, learning. And if there are no sharp transitions, then perhaps personal change is also vague. Perhaps there are cases where it is indeterminate whether someone is the same person they were years ago, whether they have changed in significant ways or remained essentially the same. And this connects to deeper issues about persistence, continuity, and what it means to endure through time. The bald man stands as a symbol of all borderline cases, all situations where reality resists the either-or structure of classical logic, where predicates fade gradually from clear application to clear non-application, passing through a twilight zone where truth becomes uncertain. And the paradox endures because it exposes a tension between the precision we expect from rational thought and the vagueness inherent in the world and in language, and no solution has won universal acceptance. Philosophers continue to debate whether to accept sharp boundaries, revise logic, relativize truth to context, or adopt some more radical approach. And the bald man remains poised between categories. Neither clearly bald nor clearly not bald in the borderline cases, a living embodiment of the limits of definition, a reminder that the world does not always cooperate with our desire for clarity, and that some questions may have no determinate answer, not because we lack knowledge, but because the questions themselves presuppose a precision that reality does not provide. And the hairs fall one by one, and baldness approaches, and no single hair marks the moment of transformation, and the paradox persists, unresolved and perhaps unresolvable, a permanent feature of the conceptual landscape we must navigate, a crack in the foundations of logic that cannot be sealed. The Bertrand's box paradox. 3 identical boxes sit before you, each containing 2 coins. The first box contains 2 gold coins, the second box contains 2 silver coins, and the third box contains 1 gold coin and 1 silver coin. And you cannot see inside the boxes, cannot distinguish them from the outside. And a box is chosen at random and opened, and 1 coin is drawn from it, also at random, and the coin turns out to be gold. And now a question is posed that seems simple, but leads to surprising confusion. What is the probability that the other coin in the same box is also gold? And the intuitive answer that most people give is 1/2, reasoning that since the drawn coin is gold, the box cannot be the one with 2 silver coins. So it must be either the box with 2 gold coins or the box with 1 gold and 1 silver. And these 2 possibilities seem equally likely, and so the probability that the other coin is gold should be 1/2. But this reasoning is wrong. The correct answer is 2/3, and this is Bertrand's box paradox, named after Joseph Bertrand, who presented it in 1889, a puzzle in conditional probability that reveals how easily intuition misleads when reasoning about random processes and conditional information. The error in the intuitive reasoning lies in treating the 2 remaining boxes as equally likely, but they are not, because the probability calculation must account for how the gold coin was observed, must condition not just on which box was chosen, but on which coin was drawn. And the key insight is that there are 3 gold coins in total, 2 in the first box and 1 in the third box, and the drawn coin is equally likely to be any of these 3. And if the drawn coin is one of the 2 from the first box, then the other coin in the same box is also gold, while if the drawn coin is the one from the third box, then the other coin is silver. And since two of the three equally likely possibilities lead to the other coin being gold, the probability is 2/3, not 1/2. Another way to see the solution is to consider all possible outcomes. There are 6 coins in total, labelled gold 1 and gold 2 in the first box, silver 1 and silver 2 in the second box, and gold 3 and silver 3 in the third box, and each coin is equally likely to be the one drawn. And we're told that a gold coin was drawn, which eliminates silver 1, silver 2 and silver 3, leaving gold 1, gold 2 and gold 3 as equally probable. And if gold 1 was drawn, then the other coin in the same box is gold 2. If gold 2 was drawn, then the other coin is gold 1. And if gold 3 was drawn, then the other coin is silver 3. And so in 2 of the 3 cases, the other coin is gold, giving a probability of 2/3. The Bertrand box paradox is structurally similar to other probability puzzles, like the Monty Hall problem and the 3 prisoners problem, where conditioning on partial information updates probabilities in non-obvious ways, where the process by which information is revealed matters as much as the content of the information, and where naive intuition fails to properly account for the structure of the problem. And the paradox illustrates the importance of specifying the sample space carefully, of identifying all possible outcomes and their probabilities, and of using Bayes' theorem or other formal tools to update probabilities rather than relying on informal reasoning. The paradox also raises questions about the reference class problem, about which population of events the observed outcome should be considered a member of, because the intuitive error involves thinking of the outcome as selecting a box type, either 2 gold or mixed, rather than selecting a particular coin. And this shift in reference class changes the probabilities, and the correct solution requires identifying the right reference class, the set of all coins that could have been drawn, and calculating probabilities relative to that set. Bertrand's box paradox has pedagogical value. It is often used in teaching probability to illustrate conditional probability, to show how careful reasoning differs from intuitive judgment, and to demonstrate the value of systematic methods like constructing probability trees or using Bayes' theorem. And students who understand the paradox gain insight into a common class of errors that arise from failing to properly condition on all relevant information, from treating distinct events as equiprobable when they are not, and from confusing the probability of a hypothesis given evidence with the probability of evidence given a hypothesis. The paradox also appears in variations, sometimes with coloured balls instead of coins, sometimes with different numbers of boxes or different distributions, and each variation tests slightly different aspects of probabilistic reasoning, but the core lesson remains the same: that conditional probabilities must be calculated carefully, that intuition is unreliable, and that formal methods are necessary to avoid systematic errors. And the paradox connects to real-world situations where similar reasoning is required. Medical diagnosis, where symptoms must be interpreted in light of disease prevalence and test reliability. Legal reasoning, where evidence must be weighed in light of prior probabilities and alternative explanations. And machine learning, where classifiers must be trained to properly account for base rates and conditional dependencies. The boxes sit on the table, indistinguishable from the outside. The gold coin gleams in your hand, and the question hangs in the air: what is the probability that the other coin is also gold? And the answer, 2/3, contradicts the intuitive 1/2. And the gap between intuition and mathematics reveals something about how we reason about chance, about how we estimate probabilities, about how we update beliefs in light of evidence. And the Bertrand box paradox remains a touchstone, a simple puzzle with a surprising answer, a demonstration that probability is subtle, that conditioning changes things in non-obvious ways, and that even questions that seem straightforward can hide complexity, can require careful analysis to answer correctly. And the paradox endures as a teaching tool, a cautionary tale, a reminder that mathematical reasoning is necessary to avoid errors that intuition cannot prevent. And the gold coin sits there, evidence that shifts probabilities, information that updates beliefs, and the calculation proceeds, formal and precise, yielding 2/3, and the intuition retreats, humbled by mathematics, corrected by careful thought, and the lesson is learned again, that probability is counterintuitive, that conditional reasoning is hard, and that paradoxes like Bertrand's box serve an essential function, exposing the gaps between how we think we reason and how we actually should reason, between the quick judgments of intuition and the slow calculations of mathematics. And the boxes remain coins inside, waiting to teach the next student, to confound the next intuition, to reveal once more that chance and evidence interact in ways that defy expectation. And the paradox persists, elegant and instructive, a permanent fixture in the pedagogy of probability, a puzzle that generations of students have encountered and been surprised by, and will continue to encounter as long as probability is taught and intuition needs correction. The Abilene Paradox: why groups choose what nobody wants. A family sits on a porch in Coleman, Texas, on a hot afternoon, comfortable, playing dominoes, and the father-in-law suggests driving to Abilene for dinner, 53 miles away in a car without air conditioning. And the suggestion is not enthusiastic, is tentative, but the son-in-law says sure, sounds good, not because he wants to go, but because he assumes others want to go, and he wants to be agreeable. And the wife says yes if you all want to go, and the mother-in-law says of course, and they all pile into the car and drive to Abilene in dusty heat, arrive hot and tired, eat mediocre food, drive back exhausted, and sitting on the porch again, someone admits they didn't really want to go, and then everyone admits they didn't want to go, admits they only agreed because they thought others wanted it, and the entire group took an action that no individual wanted, chose an outcome that everyone preferred to avoid. And this is the Abilene Paradox, described by management professor Jerry Harvey, a phenomenon where groups make decisions that contradict the preferences of all members, where collective action diverges from individual preferences, not through majority rule or compromise, but through misperception, through failure to communicate, through assumptions about what others want. And the paradox reveals that agreement is not always consensus, that unanimous decisions can be unwanted by everyone. And the Abilene Paradox shows a different kind of collective irrationality from Condorcet cycles or voting paradoxes, shows irrationality that arises from social dynamics, from conformity pressure, from reluctance to dissent. And the paradox remains relevant for understanding group decision-making, for recognizing that groups can fail not just through conflict, but through false consensus, through everyone going along with what nobody wants. Imagine the psychology of each family member. Each sits on the porch comfortable, each prefers staying home, but each hears the suggestion and thinks, well, if someone is suggesting it, they must want it. I don't want to be the one who ruins everyone's plans. I should be agreeable, go along, be a team player. And so each agrees despite preferring to stay, and no one voices their actual preference. No one says I'd rather stay home. And the group collectively creates a false impression, creates the appearance of consensus when none exists, and everyone interprets others' agreement as reflecting genuine preference rather than social accommodation. And this mutual misperception drives the group toward an outcome no one wants. And the paradox unfolds, the trip is taken, the unwanted dinner eaten, and only afterward does truth emerge. Does communication clarify that everyone preferred staying home? And the group confronts the absurdity, the recognition that they did something no one wanted through failure to communicate authentically. The Abilene Paradox differs from groupthink, where group members genuinely conform their preferences to the group, genuinely come to believe the group view. And Abilene involves no genuine preference change, involves only misperception, only assumption about what others want. And members maintain their private preferences, but suppress them out of social pressure, out of desire to be agreeable. And this suppression is the source of the paradox, creates the gap between public agreement and private preference, and the gap allows groups to pursue actions that everyone opposes. And breaking the paradox requires someone to voice dissent, to say, actually, I'd prefer not to go. And this dissent can reveal that others feel the same, can break the false consensus, but dissent is risky, is socially uncomfortable, requires challenging what appears to be group preference. And most people avoid this, prefer to go along, and the paradox persists. Visualize the Abilene paradox as a coordination failure, where the optimal outcome requires everyone to reveal their true preferences, requires honest communication, but social norms and psychological tendencies prevent this, create pressure toward agreement, toward accommodation, toward not rocking the boat. And these pressures are strongest when relationships matter, when group harmony is valued, when dissent risks social costs and family dinners and work teams and community groups all face Abilene risks. All can make decisions that no one wants, through false consensus, through failure to communicate authentically. And the paradox shows that agreement is not always good, that unanimous decisions can be wrong, that groups need mechanisms for authentic communication, need cultures that encourage dissent, need permission to disagree. One lesson from the Abilene paradox is the importance of honest communication, of creating environments where people feel safe expressing disagreement, where dissent is welcomed rather than punished. And organizations that suffer repeated Abilene paradoxes often have cultures of false harmony, have norms that discourage challenging proposals, have leaders who interpret dissent as disloyalty, and these cultures create conditions for Abilene, create pressure toward agreement, and preventing the paradox requires changing culture, requires valuing truth over harmony, requires encouraging people to voice concerns. And this is difficult, requires conscious effort, requires leadership that models disagreement, that rewards dissent, that avoids shooting messengers. Another lesson is about decision-making procedures, about how groups can avoid Abilene through structured processes, through anonymous voting, through devil's advocate roles, through explicit checking for consensus, through asking not just who agrees, but who disagrees and why. And these procedures create space for dissent, create permission to voice opposition, and reduce pressure toward false consensus. And effective groups use these procedures systematically, build them into decision-making, recognize that surface agreement may hide opposition, and these procedures are especially important for high-stakes decisions, for commitments that are costly to reverse. And the trip to Abilene is costly, is unpleasant for everyone, and could have been avoided with better communication. The Abilene paradox also appears in organizational settings, in corporations where teams pursue strategies that no one really supports, in committees that adopt policies no member wants, in groups that invest in projects everyone privately doubts. And these organizational Abilenes are costly, waste resources, damage morale, produce outcomes that serve no one's interests. And preventing them requires organizational awareness, requires training people to recognize Abilene dynamics, requires creating cultures where speaking up is safe, where dissent is valued, and many organizations fail at this. Have cultures of deference, have hierarchies, where subordinates agree with superiors even when privately opposed. And these cultures are Abilene-prone, create repeated paradoxes, and organizational effectiveness requires breaking these patterns. Some argue that the Abilene paradox is overstated, that genuine cases are rare, that most group decisions reflect genuine preferences of at least some members, and while everyone agreeing despite everyone opposing is uncommon, partial Abilene is more common, where some members oppose but remain silent, and the group pursues a course that a vocal minority supports while a silent majority opposes. And this partial Abilene is still problematic, still produces suboptimal outcomes, and preventing it still requires encouraging dissent, requires creating safety for opposition. The paradox also raises questions about responsibility, about who is responsible when groups make decisions no one wants. And the answer is everyone and no one. Everyone contributed through silence, through false agreement, through failure to voice opposition. But no one individually caused the outcome. No one individually chose wrongly. Each made a reasonable social decision to accommodate perceived group preferences. And the collective outcome is worse than any individual action merited. And this shows how social dynamics can produce results that exceed individual culpability, can create group failures that no individual intended. And avoiding such failures requires collective awareness, requires group-level solutions, requires changing communication patterns and decision procedures. The family sits on the porch afterward, hot and tired and annoyed, and someone admits they didn't want to go, and the admissions cascade. And everyone realizes the absurdity, realizes they collectively did something no one wanted, and the Abilene paradox is revealed, and laughter mixes with frustration, and the lesson is learned. The importance of honest communication, the danger of false consensus, the need to voice dissent, and the paradox remains a permanent reminder that groups can fail not just through conflict, but through excessive agreeableness, through mistaken assumptions about others' preferences, through social pressures that suppress authentic communication, and the Abilene paradox endures as a cautionary tale about group decision-making, a demonstration that agreement is not always consensus, that unanimous decisions can be wrong, and that preventing collective irrationality requires creating environments where dissent is safe, where truth is valued over harmony, and where groups communicate authentically rather than accommodating falsely. The blind sight paradox. Why some blind people can see without seeing. A patient suffers damage to the primary visual cortex, the region of the brain that processes visual information and produces conscious visual experience. And the damage is severe, destroys the tissue completely, and the patient reports being blind, reports seeing nothing, experiencing only darkness in the affected visual field. And vision tests confirm the blindness. The patient cannot identify objects placed in the blind region, cannot read letters, cannot describe colours or shapes, and by every standard clinical measure, the patient has lost vision in that part of their visual field. And yet something strange occurs. Experimenters place objects in the blind field and ask the patient to guess where they are, to point at them even though the patient cannot see them, and the patient protests, says this is pointless, says there is nothing to see, but when forced to guess, the patient points accurately, reaches correctly, identifies the location, and sometimes even the nature of objects at levels far above chance. And this ability, this capacity to respond to visual information without conscious visual experience is called blind sight, and it creates a paradox. The patient is both blind and not blind, both lacks vision and has vision, lacks conscious sight but retains unconscious visual processing. And this dissociation between conscious experience and information processing challenges our understanding of perception, challenges the relationship between consciousness and function, and raises questions about what vision is, whether seeing requires awareness, whether perception requires experience. And this is the blind sight paradox, a phenomenon that reveals that consciousness can be separated from processing, that the brain can use information without the person experiencing it. Imagine the blind sight patient's perspective, looking straight ahead, and part of the visual field is normal, contains conscious visual experience, objects and colours and shapes, and another part is blank, is darkness, is absence of experience, and experimenters place an object in the blind region, a ball perhaps, and ask where it is, and the patient says, I don't know, I can't see anything there. And the experimenter says, just guess, point to where you think it is, and the patient reluctantly points, randomly it seems. And yet the pointing is accurate, is directed toward the ball, and the patient is surprised. Says it was just a lucky guess, has no feeling of seeing, No visual experience that guided the response, and yet the accuracy persists trial after trial. And the paradox is that the patient is using visual information, is processing it, is responding to it, but is not conscious of it, is not experiencing it. And vision has split into two components: conscious experience and information processing. And these normally go together, but in blind sight they come apart. The blind sight phenomenon has been documented in multiple patients, studied extensively, and the mechanism involves intact pathways from the eye to brain regions outside the primary visual cortex. Pathways that process visual information for action and navigation without producing conscious experience. And these pathways allow blind sight patients to respond to visual stimuli without seeing them. And the existence of these pathways shows that vision is not a single unified process, but involves multiple systems, some conscious and some unconscious. And damage to visual cortex eliminates conscious vision, but leaves unconscious visual processing intact. And this dissociation reveals something fundamental about consciousness, shows that information processing is not sufficient for conscious experience, that the brain can process and use information without that information becoming conscious. Visualize vision as having multiple components. One component processes information for conscious perception, for seeing in the ordinary sense, for having visual experiences, and another component processes information for action, for guiding behavior, for spatial navigation. And normally these components work together, are integrated, and we do not notice the distinction. But in blind sight, they separate. One component is destroyed while the other remains, and the patient has action vision without perceptual vision, can use visual information for pointing and reaching, but cannot experience that information, cannot see it. And this shows that conscious experience is not simply a byproduct of information processing, but is a specific kind of processing, localized in specific brain regions. And when those regions are damaged, consciousness is lost even though other forms of visual processing continue. The blind sight paradox challenges functionalist theories of consciousness. Theories that say consciousness is defined by functional roles, by what information does, by how it affects behavior, because in blind sight, visual information performs many of its normal functions, guides behavior, enables responses, but does not produce conscious experience. And so consciousness is not identical to function, is something additional, is a specific kind of processing beyond mere responsiveness to stimuli. And this supports theories that distinguish between access consciousness, the availability of information for cognitive processes, and phenomenal consciousness, the subjective experiential quality. And blind sight shows that these can come apart, that information can be accessed and used without being phenomenally conscious. One response to the blind sight paradox accepts that it shows consciousness is separate from certain functions, from certain kinds of information processing, but argues that this does not threaten physicalism, does not show that consciousness is non-physical, only that it is a specific physical process localized in specific brain regions. And blind sight is a case where some visual processing continues without the processing that produces conscious experience. And this is compatible with consciousness being physical, being identical to certain patterns of neural activity. And the paradox shows which patterns are necessary for consciousness, shows that primary visual cortex is essential. And this is progress in understanding the neural correlates of consciousness. Another response questions whether blind sight patients truly lack conscious experience, argues that they might have degraded or partial visual experiences that they do not recognize as vision, that do not match their expectations of what seeing should feel like. And when they say they see nothing, they mean they have no clear, vivid visual experience, but they might have vague feelings, subtle impressions that guide their guesses. And these impressions might be minimal forms of consciousness rather than pure unconscious processing. And this response denies the complete dissociation, argues that some phenomenology remains in blind sight, even if it is not ordinary visual phenomenology. A third response embraces the paradox as revealing that consciousness is not necessary for many cognitive functions, that unconscious processing is far more powerful than we thought, that the mind operates largely without awareness and consciousness is only the tip of the iceberg, a small subset of mental processes, and blind sight is an extreme case, but similar dissociations occur in normal cognition, where we process information, make decisions, guide behavior without conscious awareness. And the paradox shows that consciousness, rather than being essential to cognition, is a specialized feature that occurs only in certain conditions, for certain kinds of information processing. The blind sight paradox also has implications for debates about animal consciousness, about which animals are conscious, because if information processing without consciousness is possible in humans, then it might be the norm in simpler animals. Animals might respond to stimuli, navigate environments, exhibit complex behaviors without having conscious experiences, without there being anything it is like to be them. And this makes determining animal consciousness more difficult, makes behavioral evidence insufficient, because behavior can be produced by unconscious processing, as blind sight demonstrates. The patient sits in the laboratory, the blind field tested again and again, and each time the accuracy surprises, the pointing succeeds, the guessing is correct, and the patient insists they see nothing, feel nothing, experience nothing in that region, and yet the information is there, is being used, is guiding behavior, and the paradox persists. Vision without seeing, processing without experience, function without phenomenology, and the blind sight paradox remains one of the most important phenomena in consciousness research, a real-world demonstration that conscious experience and information processing can dissociate, that the brain can use information the person does not consciously access, and that consciousness is not reducible to function, is something specific, something localized, something that can be lost while other aspects of vision remain. And the phenomenon continues to challenge theories of consciousness, continues to provide evidence about the neural basis of awareness, and continues to raise questions about what consciousness is, what purposes it serves, why it exists, and whether it is necessary for cognition or is instead a luxury, an addition, something that happens only when certain brain regions process information in certain ways. And the blind sight patient reaches into darkness and touches the object, accurate despite seeing nothing, and the paradox endures. The analysis paradox. Philosophy has long been concerned with analysis, with taking complex concepts and breaking them down into simpler components, with providing definitions that specify the necessary and sufficient conditions for the application of a term, and this project of conceptual analysis seems both important and straightforward. We want to know what knowledge is, what justice is, what truth is, and we proceed by analysing these concepts, by stating explicitly what they mean, by giving definitions that capture their essential features. Yet there is a paradox lurking here, a puzzle about whether analysis is even possible. And this is the paradox of analysis, first articulated clearly by C.H. Langford, and discussed extensively by G.E. Moore and others in the early 20th century. The paradox can be stated simply: suppose we offer an analysis of some concept. For example, we might analyse the concept brother as male sibling, and this analysis, if correct, should be informative, should tell us something we did not already know about what brotherhood consists in, should illuminate the concept by making its structure explicit. But if the analysis is correct, then the analysandum, the concept being analysed, and the analysans, the analysis itself, must have the same meaning. They must be synonymous, otherwise the analysis would be incorrect. It would not capture what brotherhood really is. And if they are synonymous, then the statement brother means male sibling should be trivial, should be like saying brother means brother, a mere tautology that provides no new information. And so the analysis cannot be both correct and informative. If it is correct, then it is trivial. And if it is informative, then it is not a genuine analysis, but merely a stipulation or a proposed change of meaning. The paradox threatens the entire project of conceptual analysis, because it suggests that analysis cannot do what it is supposed to do, cannot both correctly identify the meaning of a concept and provide new insight into that meaning, cannot be both true and interesting, and so either conceptual analysis is impossible, or our understanding of what analysis is and what it aims to achieve must be revised. One response to the paradox distinguishes between sense and reference, between the meaning of a term and what it picks out, and argues that an analysis can be informative even if the analysandum and analysans refer to the same thing, because they can differ in sense, in the way they present or describe that thing. And so the analysis brother means male sibling is informative, because even though brother and male sibling refer to the same set of individuals, they present that set in different ways, one as a family relation and the other as a combination of gender and kinship. And this difference in sense makes the identity statement informative rather than trivial. Another response appeals to a distinction between conceptual and factual knowledge, arguing that analysis does not provide factual knowledge about the world, but conceptual knowledge about our own concepts, that it makes explicit what was already implicit in our understanding, that it brings to consciousness the structure of concepts that we already possess and use, but have not fully articulated. And so, the informativeness of analysis is not the informativeness of discovering new facts, but the informativeness of self-clarification, of making our own conceptual commitments explicit and transparent. A third response, associated with Quine and others skeptical of the analytic-synthetic distinction, denies that there is a sharp line between conceptual analysis and empirical investigation, arguing that all beliefs form a holistic web where conceptual revisions and factual discoveries are intertwined, and that what we call analysis is really just careful reflection on our current best theory of the world, subject to revision in light of new evidence or theoretical considerations. And on this view, the paradox dissolves, because analysis is not supposed to be a priori or purely conceptual, but is continuous with empirical inquiry, and so it can be both correct and informative without any mystery. The paradox also raises questions about the methodology of philosophy, about whether philosophy can make progress through analysis or whether some other method is needed. And different philosophical traditions have taken different stances, with analytic philosophy traditionally emphasizing conceptual analysis as a central tool, while continental philosophy has been more skeptical of analysis, focusing instead on interpretation, critique, and phenomenological description. And the paradox of analysis has been one factor driving some philosophers away from traditional analysis toward other approaches. The paradox connects to issues about understanding and competence, because we seem to have a kind of implicit or tacit understanding of concepts like knowledge, justice, and truth. We can use these concepts correctly, can apply them to particular cases, can recognize when they are used inappropriately, and yet when asked to state explicitly what these concepts mean, to provide a definition, we struggle. And this suggests that conceptual competence does not require explicit knowledge of definitions, that understanding can be practical and procedural rather than theoretical and propositional, and that analysis attempts to convert implicit understanding into explicit knowledge, a conversion that is difficult and perhaps impossible to complete without remainder. The paradox also appears in the context of philosophical disagreement, because philosophers have been offering analyses of key concepts for millennia, and yet consensus remains elusive. Different philosophers provide different analyses of knowledge, of justice, of truth, and it is not always clear how to adjudicate between competing analyses, whether by appeal to intuitions about particular cases, by considerations of theoretical simplicity and fruitfulness, or by some other standard. And the lack of agreement raises the question of whether these concepts have determinate meanings that analysis can discover, or whether they are vague, contested, or essentially contested, such that no single analysis could capture all the ways they are legitimately used. The analysis paradox remains a puzzle at the heart of philosophy, a question about what philosophy is doing when it offers definitions and analyses, whether it is discovering pre-existing meanings, stipulating new ones, or engaging in some more complex activity that combines elements of discovery, stipulation, and rational reconstruction, and the paradox has not been definitively resolved. Different philosophers find different responses more or less compelling, and the debate continues, with implications for how we understand the nature and methods of philosophical inquiry. And the concept sits there, waiting to be analysed, inviting us to state its essence, to specify its conditions, to make explicit what we already implicitly know, and yet the analysis, when offered, seems either to tell us nothing new or to change the subject, to offer a different concept rather than clarifying the original one. And the paradox persists, a thorn in the side of analysis, a reminder that understanding is more elusive than it appears, that the gap between knowing how to use a concept and knowing what it means is wider than we thought, and that philosophy, despite its ancient commitment to clarity and definition, to making the implicit explicit and the confused clear, may be chasing a goal that is inherently problematic, inherently paradoxical, a goal that recedes as we approach it, that becomes more obscure the more we try to illuminate it, and yet we continue to analyse, to offer definitions, to seek clarity, because the alternative, giving up on understanding, seems worse.